Vernier caliper. In this video we will learn about vernier caliper. Vernier caliper is a measuring instrument which can be used to measure height, thickness, depth and internal and external diameters of the various components. It works on the principle of difference in two scale. It can measure dimensions accurately up to 0.02 mm or 0.001 inches. Where 0.02 mm or 0.001 inches is the least count of the vernier caliper. Let us see its various parts in detail. It has main scale, vernier scale, external measuring jaws, internal measuring jaws, lock screw, and depth measuring bar. Main scale. Main scale has a markings which are engraved on it. On top, the markings are in inches and on the bottom they are in mm. Vernier scale. Vernier scale has a marking on top and bottom. Top scale is for taking readings in inches and bottom scale is for taking readings in millimeters. There are two types of vernier scales. Forward vernier, backward vernier. If on the bottom there are 50 divisions, whose total length is equal to the length of 49 division on main scale, this type is called forward vernier. On the other hand, suppose 50 divisions on vernier scale are equal to 51 divisions on main scale. Such a vernier is called backward vernier. In this video we will discuss about forward vernier. External measuring jaws. In external measuring jaws, there is a fixed jaw which is a part of main scale and a sliding jaw which is attached to a vernier scale. It is called sliding jaw because it slides with vernier scale. These jaws are used for measuring external dimensions, such as outer diameter, length, and thickness of components. Internal measuring jaws. Here also, there is a fixed and a sliding jaw. These jaws are used for measuring internal dimensions, such as inner diameter, slot dimensions, and distance between two parallel surfaces. Lock screw. On top of vernier scale there is one lock screw, which helps in clamping the movable jaw in a particular position after jaws have been set accurately over the job being measured. This arrests further motion of the movable jaw so that the operator can note down the reading in a convenient position. Whenever the vernier slides over the main frame, a depth measuring blade also slides in and out of the beam of the caliper. This is a useful attachment for measuring depth to a high degree of accuracy. Now let us see how the least count of vernier instrument is calculated. As we discussing forward vernier scale caliper, we knew that 50 divisions on the vernier scale is equal to 49 divisions on the main scale, equating both. 50 vernier scale divisions equals 50 minus 1 main scale divisions. Therefore, 1 vernier scale division equals 50 minus 1 divided by 50. 1 vernier scale division equals 49 divided by 50 millimeters. Therefore, we knew least count equals 1 main scale division minus 1 vernier scale division, which is equal to 1 minus 49 divided by 50 millimeters, which is equal to 0.02 millimeters. Therefore, the total reading will be equal to main scale reading plus vernier scale divisions into least count. Let us see how to take measurement of a component using vernier caliper. First, completely close the vernier caliper. These are the surfaces where you can take a measurements. And you can also see couple of gaps. These are not the places to take measurements. Now let us take measurement of an object. When we hold this object between the two jaws, we first take reading from the main scale, and we can see that 0 of the vernier scale coincides exactly with 40th division of the main scale. In this case the size of the object is 40 millimeters. No vernier scale reading is required since the 40 mm line of the main scale coincides with 0 of the vernier scale. Let us take another example. In this case again hold the object between the two jaws. In this example we can see that the size of the object is not exactly 40 millimeters. It is between 40 and 41 millimeters. In this case we require vernier scale to get accurate measurement. But this time I'm only going to draw the main part of it first. Now you see the marked number from 0 to 10. Each of these numbers represents the tenth of the millimeters. We can see one of the vernier scale mark lines up better than others. Let me give you a hint where to look on the vernier scale, where mark lines up. You see how our zero line of the vernier was more than halfway between the marks. That means the vernier scale will line up more a little past halfway. Now we can see that the line which lines up better than other. It looks like 6 is lining up better, the 6 means 0.6 millimeters. But this vernier caliper can measure more accurate than that. Let me redraw all the lines. Now see that the line before 7 lines up better. Now what is the value of that point? We already knew least count of the vernier is 0.02 millimeters. That means each of these divisions are 0.02 millimeters. Now let us count. This 6 would be 0.6, next point. 0.62, next point. 0.64, next point. 0.66 and the coinciding point will be 0.68. Therefore, the length is main scale reading, which is 40 millimeters, plus this 0.68 millimeters, which is equal to 40.68 millimeters. If you are still confused, the another easy way of measuring is to see which line of vernier is coinciding with main scale. Here in this case at 34th line, therefore 34 is our vernier scale division. And you can remember we already seen total reading is equal to main scale reading plus vernier scale reading into list count. This will give you 40.68 millimeters.
Micrometers are produced in various precisions, both in metric and English units. In every case, it is the thread pitch of the spindle screw that makes each type different. The thread pitch is the distance between two adjacent thread crests. In this example, the thread pitch of the micrometer spindle screw is precisely 1/2 millimeter. Each revolution of the thimble moves the micrometer spindle 1/2 millimeter. The micrometer has a reading line on the sleeve. The vertical graduations on the top of the reading line each represent a single millimeter. The vertical graduations below the reading line indicate 1/2 millimeters. The beveled edge of the thimble is graduated into 50 divisions. Since a single revolution of the thimble moves the spindle 1/2 millimeter, each thimble graduation equals 1/50th of 1/2 millimeter, or 1/100th of a millimeter. The thimble is rotated and the spindle advanced until the feature is held between the anvil and the spindle face. To read this micrometer, add the number of millimeters and 1/2 millimeters visible on the sleeve to the number of hundredths of a millimeter indicated by the thimble graduation, which coincides with the reading line on the micrometer sleeve.
Dial indicator is a very important comparator used in mechanical industrial measurement applications. In this video we'll learn about dial indicator. This video will cover the following. 1. Working principle of dial indicator. 2. Its construction. 3. Working. 4. Applications. 5. Advantages and disadvantages. If you are new to ADTW, click on the subscribe button below and turn on the notification to get all the updates. Let's start. Working principle of dial indicator. It operates on the principle that a very slight upward pressure on the spindle or plunger at the contact point is multiplied through a system of gears and levers, and it is indicated on the face of the dial by the pointer. Dial indicators consists of a body with a round graduated dial and a contact point which is connected with a gear train so that pointer on the dial face magnifies and indicates the amount of plunger movement. Construction of dial indicator. Dial gauge consists of following parts. Circular dial body. Pointer or indicating hand. Round graduated dial. Revolution counter. Bezel. Bezel clamp. Dust cap. Stem. Plunger, which is subdivided into spindle and contact point. In the side view we can see other parts: crystal, back, mounting lug. After opening the body of dial indicator we can see internal parts, and those are rack, rack guide, gear train, hairspring, and coil spring. Working of dial indicator. Before we see the working of dial indicator, let us first understand how the magnification is achieved with the help of gears. Consider two gears A and B. These gears are mashing with each other. The number of teeth on the gear A is less compared to gear B. The smaller gear A is called pinion. When we rotate pinion by 1 revolution, the gear B rotate through a small angle. This depends on the gear ratio. Now, suppose we rotated gear B by 1 full revolution, the number of revolution of pinion is more. With this basic understanding, now we can see how the magnification of the plunger is achieved in the dial gauge. To obtain the necessary high magnification ratio in this instrument, gear and pinion arrangement is used. By arranging the gear train in a manner similar to a clock movement, there is a plunger which is a perfect sliding fit in its own bearings. This carries a rack which accurately meshes with a pinion A. The rotation of the plunger about its own axis is prevented by a pin attached to it, which is located in a slot in a rack guide. In order to keep the plunger in an extended or normal position, a light coil spring is employed. A small movement of the contact point causes the rack to turn the pinion A with which it is meshed. A large gear B is attached to the same spindle as pinion A. The gear B is further meshed with a pinion C, which thus magnifies the movement of pinion A. Attached to the second pinion C is another gear D which meshes with a third pinion E, mounted on the same spindle as the indicator pointer. This magnification is further enlarged at the tip of pointer by an amount depending upon its length. In order to take up backlash, a light hair spring H is always fitted to the dial gauge gear trains by meshing a gear F to pinion E and attaching spring with gear F, also to prevent gear backlash. The gears are precision cut and the movement assembly resembles that of high-grade watch. After final assembly, each dial gauge is thoroughly tested and checked and properly calibrated by either a calibrated micrometer head or by the use of slip gauges. If the pointer moves more than 1 revolution, a revolution counter is also incorporated, which will correctly indicate the number of revolutions made by the main pointer and thus enable a complete reading to be made when the gauge is used for direct measurement. Also, we can rotate the round graduated scale to set the pointer to 0. In some dial indicators, 2 range pointers are given on the bezel, which are used to set the range. Applications of dial indicator. 1. Comparing 2 heights or distance between narrow limits. 2. To determine the errors in the geometrical form such as ovality, roundness, and taper. 3. For taking accurate measurements of deformation such as intention and compression. 4. To determine positional errors of surfaces such as parallelism, squareness and alignment. 5. To check the alignment of lathe centers by using a suitable accurate bar between the centers. 6. To check the trueness of milling machine arbors and to check the parallelism of shaper arm with table surface or vise. Advantages. 1. Dial indicator is the most flawless tool in taking linear measurements. 2. Moreover, dial indicators are also be used to measure several deviations by aligning with some other attachments. 3. Due to small tolerances, the size of the tool is very compact and thus, it can be used seamlessly in mass production. 4. Out of roundness, the amount of taper can also be measured efficiently by dial indicators. 5. The tool is very efficient to assure the quality of a work piece. 6. Dial indicator is also useful in dimension control. Disadvantages of dial gauge. 1. The precision of dial indicators often lost due to the vibration of machinery. 2. Another crucial disadvantage of the tool is the parallax effect. 3. Space constraints can lead to installing the tool at an angle, due to which precision of measuring device is lost. Hope you have understood the dial indicator. If you want more in-depth videos like this, then subscribe this channel and click on the bell icon to get notified for every special video we upload. Also, if you have any doubt or opinion, comment it below. And help us by sharing this video with your friends.
Friends, now I will tell you type A quick check. Type A quick check look like this. And it is designed for all variable instruments. So first of all, I tell you what is variable instruments, like vernier caliper, like micrometer, bevel protector, puppy dial, plunger dial, all those instruments which gives their output in a variable form. So these kind of instruments called variable instruments. And type A quick check is designed to develop skill for variable instruments. So like vernier, anyone can develop his skill on OD jaws, ID jaws, depth bar, and step also. So you can see, similarly, you can use any kind of micrometer, and user can develop his measurement and inspection skills in different range of micrometer from small to big one. And say for puppy dial, you can use these steps. For plunger dial, again you can use this step for small and these steps for big ranges. For angle, you can use like this, bevel protector. You can use like this for 90 degree. You can use like this for 180 degree. So one can use his skill and develop his skill to understand and to see the difference of the measurement. So I'll tell you once again, type A is designed to develop skills of various measuring instruments with their different ranges, least count, type, profile, mechanical equipment, digital equipments, and with their different functions. How anyone can build their skills to check on different sizes or different least count, like this. Thank you.